fifth and final note of Unit 5 on exponential relations. This note, we will be discussing modeling exponential growth and decay. So the following relation is used to model exponential growth or decay. So that formula is P equals I times B to the power of T. P, in this case, is the population. I is your initial amount. T is the time. And B is the growth rate if it's greater than 1, or the decay rate if we have a fraction or a decimal. So again, remember what this means here is that B is between 0 and 1, and for B to be between 0 and 1, that means it's a fraction or a decimal. Fraction or a decimal. Okay, so growth and decay rates. So in order to figure out what your growth or decay rates are, so if a population increases by 5%, how can we display this as a growth rate? So anytime you have a growth, okay, that means it has to be greater than 1. So what we actually need to do is we just need to take 1 plus the rate it gives us, or the percent it gives us. So 1 plus 5%. But in order to add these two together, we need our percent to be in a decimal. So in order to go from, and I'll just write this as a note up top, so percent to a decimal, what you're going to do is divide by 100. Okay, so you're going to take the decimal and divide by 100. So if we do that, we will get 1 plus 0.05. Add those together, we get 1.05. So that is our growth rate, which means that is our B value. Okay? If we are decreasing, on the other hand, which means we have a decay rate, that means we need to subtract. So again, we're starting with 1, and we're subtracting the percentage it gives us. So that percentage is 2.5. But again, we can't actually subtract the percent. What we have to do first is turn it into a decimal. So again, by dividing by 100, we would turn it into a decimal. We would get 0.025. Okay, so, oh, and I put plus. That should be minus. 1 minus, again, the minus is because we're decaying. Do that on your calculator, you will get 0.975, which would be your B value for this situation. Okay, so it's always 1 plus or 1 minus, depending on if it's growth or decay. So for example, let's look at growth here. So hoping to prevent extinction, 75 African bat-eared foxes were moved to an animal reserve in Africa. The fox population increased 15.8% each year over a 10-year period beginning in 1997. Write an exponential growth equation to model this relation where P is the population and T is the number of years after 1997. Okay, so this is where I'm not going to zoom all the way out, but this is where you want to really reference that general equation that I gave you, because it tells you what all of these pieces mean. All we have to do basically is take the information we're given and sub it in to that general equation. So P is going to be our population, so that's going to stay the same. I is our initial amount. So we go back to our question, and we can see that we started with 75 of these foxes, so that would be our initial amount. Okay? In order to find our B value, we're preventing extinction, right? And we can see that the population is increasing. So that means we need to add, right? We start with our 1, and we're going to add the decimal version of this percent. So 15.8% divided by 100 is 0.158. And we are going to also leave that t, okay? Because t is going to represent the number of years after 1997. Okay, so this is our general equation. It has all the pieces that we need. It has population, we subbed in initial amount, we figured out how to calculate our growth factor, and t is the time period that we can solve for. So now using that equation, part B says how many African bat-eared foxes were present after 5 years? Okay, so it's telling you 5 years. Well, 5 years is a time period, right? So that means we need to sub in 5 for our value of t here. So we take our original equation here. I'm going to simplify it by adding these together. 1.158 to the power of 5. Okay, and that power of 5 again comes from the question. So all we have to do is know how to type this in on our calculator, right? So we know that we have to always follow BEDMAS. And again, you might want to just make yourself a little note. Make sure you remember. That means we have to simplify that exponent first. So 1.158 to the power of 5 equals times 75 gives us, and it's not going to be a whole number, so it's going to be approximately 81 foxes. Okay, so after 5 years of these foxes being at this reserve in Africa, the 75 increases to 81. Okay, the next question says, how many foxes were present at the end of 10 years? So again, it's telling you 10 years, so that's a time period. Okay, so that means we need to sub in that value for t. So we continue with that same equation because that's our general equation. Nothing changes other than the time period. So now we have to do 1.158 to the power of 10 times 75. That means that there are approximately 88 foxes after 10 years. So you can see that we're steadily increasing, right? We started with 75. After 5 years, we have 81. After 10 years, we have 88. And we know that because we know how they're growing each year. They're increasing by 15.8% each year. Okay, so let's look at an example of decay. So it says a cattle farm with a population of 240 cows is declining by 3.4% each year. So again, keyword there, declining, right? So we know this is going to be a decay. Write an exponential decay equation to model this relation where P is the population and N is the number of years. So again, we go off of that original equation of P equals I times B to the power of T. So it still wants us to have P represent population. Our initial value here, again, we take that right from the question. Our original population is 240 cows. We are decreasing, so we know that has to be 1 minus the percent as a decimal. So in order to turn that into a decimal, again, we're dividing by 100, which would give us 0.034. Put that into our equation here. And instead of to the power of t, it would like us to use the variable n. Okay, and we could simplify this equation a bit further, right? We could actually do that math. So 1 minus 0.034 is 0.966. And again, that's to the power of n. Okay, so the question asks us, what will be the expected cattle population after 5 years? So again, it's giving us a time period, right? Which is our n value. So all we have to do is sub that value into our equation and solve. So everything remains the same except our n is now 5. Remembering to use BEDMAS, doing 0.966 to the power of 5 times 240. On your calculator, you will get approximately 202 cattle. Okay, and that is the amount after 5 years. Okay, so this basically focuses on creating those equations. So we're just going to continue. We have one last page. Excuse me. All right, so again, we're still looking at this exponential growth and decay, but we're going to talk about some specific instances that you will see come up multiple times in this unit. So the first is doubling. So doubling time is the time required, and I realized I'm not ready to edit this. There we go. Doubling time is the time required for a quantity to double in size. Okay, so you have, say you have one, what do you want? One ice cream. Doubling would obviously be 2 ice creams. So when the base of an exponential function or an exponential relation is 2, the relation is describing a doubling. Okay, so this equation, P equals PO times 2 to the power of T over D, is used to determine the population P after time T, where D is the doubling period. So D is how long it takes for it to double, doubling period. And PO is the initial population. So again, it's just confusing you mostly, but PO is just the same thing as I in the examples we just looked at. Okay, so the only thing that's really new here is we don't have to find our growth rate. Okay, if we're doubling, the growth rate is always going to be 2. Okay, and the D value there that we're going to be dividing T by is just the amount of time it takes for something to double. So I think it'll make more sense with an example. So it says a bacteria culture began with 7,500 bacteria. Its growth, and again, I'm underlining growth because I need to know, is this a growth or decay? So its growth can be modeled using this equation. N equals 7,500 times 2 to the power of T divided by 36, where N is the number of bacteria after T hours. From the equation, what is the doubling time? So remember, the doubling time is just D. So in our equation, 36 is in the spot where D would be. So our doubling time is 36 days. So that means it takes 36 days for these bacteria to double in size. How many bacteria are present after 36 hours? So it's giving us, again, it's giving us a time, right? So that means we need to plug 36 in for T. So again, everything in my equation remains the same, other than the fact that I'm getting rid of my one variable, right? So 36 divided by 36. Okay, well, 36 divided by 36 is just 1. So we have 7,500 times 2 to the power of 1, which is equal to, 2 to the power of 1 is just 2, right? So 7,500 times 2 is 15,000 bacteria. Okay, so what that means, it asks us how many bacteria are present after 36 hours, which again means that I messed this up, and this should be hours, not days. So it doesn't take 36 days for them to double, it actually only takes 36 hours. So if it takes 36 hours to double and we're figuring out how many are present after 36 hours, that's just one doubling period, right? So 36 divided by 36 gave us that 1. So the next question says, how many bacteria are present after 72 hours? And how does this relate to the doubling time? So we'll start with the first part. Let's figure out how many were present after 72 hours. So again, you just keep your equation the same, except instead of T divided by 36, we now have 72 divided by 36. Okay, so the first thing we need to do is we need to simplify that exponent. So 72 divided by 36 is 2. Okay, well, 2 to the power of 2 is 4, and I'm showing you all of the steps here. 4 times 7,500 is 30,000. Okay, so there's 30,000 bacteria present after 72 hours. And how does this relate to the doubling time? Well, we can see that 72 represents 2 doubling periods. And that would be equals 72 hours. Okay, it is kind of a confusing concept, so make sure you ask questions if you're confused. All right, so exponential decay. So our other special case that we'll see come up multiple times is something called a half-life. So what a half-life is the time it takes for a quantity to reduce to half its size. So up above, we were talking about how a population would grow to double. This is when you have one and it's getting reduced to half, okay? So when the base of an exponential relation is 1/2, the relation is describing a half-life. So m equals mo times 1/2 to the power of t over h is used to find the total mass, which is m, of a decaying substance after time t, where h is the half-life and mo is that initial mass. So again, we're using different variables here so that you don't get them confused, but mo is essentially the same as I, h is essentially the same as d, right? It's the same thing as what we just looked at above. It's just representing a half-life instead of a doubling period. So again, a half-life is how long it takes to get to half of its original size. So an example here. So radon has a half-life that can be modeled by the relation O times 1/2 t to the power of 25, where m is the mass of material, in milligrams. From the equation, what is the half-life of radon? So again, we're just looking at the equation. We know that the half-life is the h, and we can see that 25 has been subbed in for h. So that means that the half-life of radon is 25 days. And this one is in days because I can look ahead and see that my other questions are in days. Okay, so it says how much of a 4 milligram sample is left after 63 days. So this is giving us two pieces of information, right? Because we actually weren't given an initial amount, that MO. So our question has to give that to us. So we're actually making two substitutions here. We're still trying to solve for that total amount, that just M all by itself. So we're leaving that as our variable. We're replacing MO with 4. It's always going to be times 1/2 because it's a half-life question. In this case, it's going to be to the power. The time period it gives us is 63, and that is over 25. Okay, so unlike the first question we did on this page where we got a whole number, you won't always get a whole number, right? In this case, we're going to get a fraction or a decimal as our power. So we have 4. Again, we need to make sure we're following BEDMAS here, so we're simplifying that power. 63 divided by 25 is approximately 2.52. Okay, our next step would be to do 1/2 to the power of 2.52 equals times 4, and you should get an answer of approximately 0.68, and we're dealing with milligrams here. Okay, and we're not going to actually worry about this part C. We're not going to get into it. Okay, so the main things here, when we're doubling, the growth rate is always 2. we need to divide by that doubling period in our exponent. When we have a half-life, we're decaying, we're reducing to half of our initial size. So our B value from the last page, our decay rate is always going to be a half, and we need to divide our time by the amount of time it takes for a substance to reach its half-life. Okay, so this is the end of our fifth and final lesson for Unit 5 on exponents.